Draw the curves for it first and then think about it. This is going to be on the y-axis. If you're rotating around this way, the slices are going to be the other direction from what we just did. So it's going to be dy because you're rotating around that axis that's vertical like that. If you graph this, well, you could graph it the other way here. Y equals negative x squared plus 1. So it's 1, and it's a parabola that opens down like that, right? And you're looking at this right here, right? This area in here. And you're rotating that around. So it's going to look like a cup, again, the same kind of shape we had before, I think. Okay? Or a bullet. Or a bullet. If you want to find this, though, if the slices are that way, the thickness of each slice is like one of these discs here. The thickness of one of the slices is dy. And you need to know this, you need to express the function the other way. The radius is right here, right? The radius is, this has to be expressed the other way. This has to be expressed as x squared equals 1 minus y. X equals plus or minus square root of 1 minus y. Except we only really need the positive side because we only need this side, right? We don't need both sides. So you need to have this as square root of 1 minus y. That's the function you need to use here because you're looking at the heights from the y-axis. You have to express it as x as a function of y, not y as a function of x. And you need to go from 0 to, this is a 1 up here. So this is going to be from 0 to 1. The radius of each of the discs is square root of 1 minus y. But you need to square that and multiply it by pi. It needs to be dy here. Again, you can do that numerically. You can do it analytically, whatever. Again, this one maybe is okay because you square that, you get 1 minus y dy. If you're doing it analytically, you have y minus a half y squared. From 1 to 0. 0 is easy to do, so that one's not that hard to do analytically, but again, you can check it on the calculator and do it both ways to make sure. What does that give you? 1 squared times a half. This is a half, and 1. Yeah, because you get 1 minus a half, right? This is a 1 minus a half times pi. So this should be pi over 2, half of pi. All right. Yep. Using washers. You have a hole in your disc. Is rotated about the. Oh, I see what you're saying. What? Oh, you mean this is where the hole punch is on your handout? What are the chances of that? That's it. 50-50. It's good. I'm glad you're thinking like that. Okay, so the thing here though is that okay, let me show you something here though. I'm going to first of all just what's the first function? 4 minus x squared. 4 minus x squared. This is valuable time. What we've done up till now is go right down to the axis here, right? So what we've done is things like this. We've done something solid like this, where you are doing all the slices from one end to the other here. If you have, and you're just using the area, remember the area of the side is just the height of the curve squared times pi. That's the area of the circle. If we make it the area between two curves, so let's just make it, no, that's no good. This one. If you make this one into a 1 now, it's going to mean you're doing the area between two things here, and let's just ignore that little bit there for a second. B, we could move back here a bit so that it just ends right there somewhere. Close enough. Whatever the intersection point is there. If you have the area between two things, you're going to have to view them as washers like this, so that you're doing the volume of these washer shapes from one end to the other. How do you find the volume of that type of shape? Came out wrong? Shape? I don't know. Is it something you said or something I said? People at home are going to think I'm insane because they can't hear any of what you're saying, right? That doesn't mean I'll start talking louder now. What? How do you? Somebody who actually wants to answer this question, maybe? What? Hang on! Don't steal his.
I'll go.
No, see, look what you did. He was going to answer the question, and you muscled right in there.
Okay, so you take the first one and you subtract the second one.
What do you mean?
On the first, you take the higher up one.
Yep.
And subtract the lower one.
When do you subtract? If you want the volume of this washer, can you subtract the two radii and then square them and times by pi? Yeah, it's a no-no, because that would give you a circle that has this radius, and it would be just a circle right here. You can't subtract the two functions first. You need to figure out the area of the big circle, and then figure out the area of the small circle, and subtract those two areas. That gives you the area of this washer shape left over. That's what you integrate. Okay, when it's washers, you have to subtract the two circular areas. It's exactly the same volume formula. You just have to think of how you find the area of a washer shape like that, of that circle with a hole in it. Okay, so now for this one that I gave you, and this is probably what I should have started with, is just a straight line as the other function, but I didn't. What did I put in as the other function? 2 minus x. 2 minus x. So it's like that. It's the same thing. It's just that your inside radius is, we're going to talk about the inside radius and the outside radius. If you have something that is circular but there's two radii, you can talk about the inside and the outside radius. Which one is which here? The radius from the center all the way to the outside is which one? F of x, right? 4 minus x squared. The inside radius is this 2 minus x, g of x. But it's going to give you this strange shape where there's a hollow cone-shaped space in the middle. Because I didn't put this to the right. This should go to, what, 2 or something? All right? And then you're still just summing up the volume of all of those things all the way from there to there. If you set up the right cross-sectional area, it's exactly the same. All right? Let's capture a picture of that we can use. That is a cool shape. I see why you said it's an eyeball now. Oh, this is kind of, what is going on here? Why doesn't it? Oh, I'm doing the wrong thing. That's what I'm doing. Not paying attention. I was moving the wrong slider here. This is the one. Okay. Okay. They get to be nothing here, right? Because they're barely, there's no difference in either of the radii, and down here as well, right? Collapses on nothing here, but here it collapses on these rings. But you can still, you express the volume of any one of those things. Okay, let's, simple cylinder. How are they calling that a simple cylinder? Oh, that's because that's what it was to start with. All right. Figure out the volume of that and then compare to. That would certainly help labeling them appropriately. So you call one F, call one G, and then the area of a cross section. Area of that washer shape or the cross sectional shape is pi times the outside radius squared minus pi times the inside radius squared. You can call them R1 and R2. Some people call the outside radius capital R and the inside radius small r. It helps to set up the area formula first. If you just say, here's the area of a cross section, it's pi times f squared minus pi times g squared. Or, in other words, you could put the pi outside of the whole thing, right? You could factor this pi out, but I will not do that right now. This is, what's f? It's 4 minus x squared. Squared minus pi times g is 2 minus x. 2 minus x squared. That's the area. So then the volume is integral from, I guess, where it intersects at -1 up to 2 of that expression right there. Pi times, okay, take that thing and enter it as is in the calculator, or work it out analytically.